Okay, Assalamualaikum. Today we continue with the other topic, which is confidence region and simultaneous comparison of component means. From the previous lesson, you have learned how to conduct the test, which is the Hotelling T-square test and likelihood ratio test, to know whether the mean vector is the plausible value for the mean multivariate population, right? So now we will see whether the mu naught ataupun the mean vector tadi tu lies in the confidence region of ellipse or not, using the value of the confidence region. Actually kita guna konsep yang sama, which is we test for the distance square. Distance square, whether it is lies in the confidence region or not. So from that we can say that the mean ataupun the mean vector mu naught is lies within the confidence region. So we use the concept of T here, T square, which is dipanggil juga another name adalah generalized squared distance, right? And multiply x bar minus mu naught. X bar dan mu naught is the vector. Transpose multiply the inverse of covariance matrix, multiply vector x bar minus vector mu naught. If the square distance ataupun t square is less than the value of c square, which is the f distribution, multiply with p n minus 1 divide n minus p. If the square distance less than the value of c square, so we can say that the mu naught tadi, the mean vector, is lies in the ellipsoid region, confidence region of ellipsoid. If not, kalau t square more than the value of c square, so we saying that mean vector mu naught is not in the confidence region. Simple. Alright, P here adalah number of variables involved, and adalah number of observation or sample size. We see the example from your textbook. Example from your textbook, example 5.3. Actually, example here is from the data of the radiation from microwave in example 4.10 and 4.17 before this. So from here, X1 dekat sini sebelum ni adalah radiation with door closed, and X2 adalah radiation with door open. But now dia buat transform sikit, power the x1 power of 1/4 dekat situ. Dia transform sikit. Alright, so from here we have the new x1 and then the new x2, and then given ataupun you can calculate the value of x bar vector, mean vector. You can calculate the variance covariance matrix, dan you boleh cari the inverse of the matrix. Alright, so from here we want to know, let's say we want to know this mean, this mean 0.562 and 0.589 ni lies in the confidence region of ellipse or not, we first of all calculate the value of square distance of ataupun or t square, and then compare dengan distribution of f. Okay, so here dia punya n sample size is 42. Okay, x bar that we calculate before this is the variance covariance inverse matrix. Okay, this is x bar minus mu naught. Okay, so now we want to test this main vector, these two main vector. So replace sahaja dalam formula of t square. Okay, calculate using the matrices. You can use calculator. And lastly, you will get 1.3. Nanti try to check the value is 1.3. Is it true or not? Okay, 1.3. So next step, we need to compare with c square. Okay, so c square is the f distribution multiply dengan p n minus 1 divide n minus 2. Okay, sorry, 2 because of the p tadi tu, n minus p. Okay, alright, and then the answer will be 6.62. So seems here the value of t square tadi is 1.3 and the value of c square is 6.62. So t square less than the value of c square means that we can say that the mean vector, which is 0.562 and 0.589, is in the confidence region of ellipsoid. Okay, next one is how we create the ellipsoid. So first of all, you need to know the axis of the confidence ellipsoid. Okay, this is the formula. Okay, beginning at the center x bar, we find the axis. We can find the axis, the major axis of the ellipse dan juga the minor axis of the ellipse using this formula. Okay, ini adalah ellipse. Okay, so from here lah kita we want to find the axis tadi from the center. Center here adalah nilai x bar. Right? So this is the major axis. This is the minor axis that we can calculate from this formula. So using the formula, we need the value of lambda dan juga the lambda, which is the eigenvalue, and its corresponding eigenvector ei. Okay, let's see how we use the formula. Okay, so let's say the center of x bar, using the same example tadi. So the mean matrix is 0.564 and 0.603 at the center. Okay, so we want to know the coordinate of the major axis dan juga minor axis. So we start here. The center of the ellipsoid, which is the value of x bar 1 and x bar 2. Okay, so kita nak tengok how to find the major axis given the eigenvalue is 0.026. Okay, so just replace using the formula here, square root of the eigenvalue, and this is the corresponding eigenvectors. So last kali you akan dapat, bila you dah solve here, so you akan dapat dua coordinate 0.609 and 0.648. Another coordinate is 0.519 and 0.558 in here and here. Okay, ini adalah major axis. Because of here kita buat dua coordinate. Okay, using the first one, using the eigenvalue 0.026. Another eigenvalue is 0.002. So this is the minor axis. Using the formula, the same formula, last kali you will get these two coordinate, which is the minor axis here. Okay, that is the way how you can create the ellipsoid. Okay, next we proceed with the simultaneous T-square intervals. This is the way how you find the confidence interval actually for a multivariate population. Okay, so before this, as I briefing you in the previous lecture, that we also can make the conclusion about the plausible value of the mean vector using the confidence interval. Right, sama juga here. We can in previous lecture, I had a briefing about the confidence, how we make the conclusion about the plausible value for the mean for the univariate. Sama juga untuk multivariate population, we also can make the conclusion about the plausible value of the mean vector using the confidence interval. Okay, so this is a formula. Because of we have a several of x, right? So we also have the several of x bar that we need, ataupun several of mu that we need to see whether that mu is the plausible value for the mean population of the multivariate. So here we have, because of that, namanya simultaneous T-square interval. Okay, so this is the formula to calculate the confidence interval untuk mu1, mu2 until mu p, because of we have p variables. Okay, the formula will be x bar plus minus square root of the f distribution. Here is the c square actually, then multiply dengan standard deviation square root of S11 divide dengan small n. Okay, S11 here adalah the variance of the first variable. Okay, so tapi kat sini kita ada square root, so you kena square root kan variance of first variable divide by sample size. Okay, sama jugalah you kena buat for every for each of the mu. Okay, so kita akan dapat confidence interval, simultaneous confidence interval for each mu. Okay, let's see the example. Okay, so recall from the example 5.2 in your textbook. 5.2 example point 2 ada dekat page 214 in your textbook. Okay, so we recall this example. From there, actually the value of h0, we need to test the value of the mean vector is 4, 50 and 10, and h1 mean vector transpose of the mean vector not equal to 4, 50 and 10. And then given the matrix of x bar is given there, and also the variance covariance matrix. So from this matrix, from this vector, we know that x1 bar is 466, x bar 2 45.4, x bar 3 is 9.9, and from the variance covariance matrix, the diagonal will be the variance of each variable, which is 2.879 is the variance for first variable, 199.78 is the variance for the second variable, and 3.6 STA680 is the variance for the third variable. Okay, we need this value to calculate the simultaneous confidence interval. Okay, let's see the formula. Okay, so each of the confidence interval that we need to calculate here, okay, we need the value of this distribution, which is the value of c square here, n minus 1p divided n minus p, multiply the f distribution with confidence with degree of freedom of p and n minus p. So first we find this distribution first. The value here is 10.5953. So after this you can check the f table and then make sure you get this answer. Okay, so apply the formula of the simultaneous T-square interval tadi. So just masukkan, replace the value here. Make sure you know how to get the variance ataupun standard deviation for the first variables. Macam mana nak dapatkan second the variance for the second variable and the third variable. Lastly, you will get this value untuk x1. The confidence of x1 will be 3.4050 and 5.8750. Okay, macam mana you nak interpret the value? The concept sama macam before this. You can say that we are 95% confidence that the value of mu1 lies between these two intervals. And then you can say that we are 95% confidence that the value of mu2 lies between these two confidence interval. Okay, same for mu3. Okay, another conclusion that you can make adalah about the plausible value of mean tadi. So from here you can see that the value of a confidence interval for mu1 is 3.4 and 5.87 here. Okay, so yang kita nak test tadi hash knot, dia punya value for mu1 is 4. So we can see here 4 lies between the interval of mu1. So we can say that mu1, which is 4, is in the interval of mu1. Okay, and then 50 lies between the interval of mu2, and 10 lies between this interval of mu3. So apa kita boleh conclude kat situ? We can say that mu vector tadi hash knot, okay, mean vector 4, 50 and 10 is a plausible value for the population mean. Okay, itu adalah untuk simultaneous interval. Okay, another method is the Bonferroni method. Okay, this method actually we use the same concept here. We use the Bonferroni method also to find the confidence interval for the population mean, mu1, mu2 and mu until mu p. But for simultaneous T-square interval tadi, we use the distribution of f here, right? But for Bonferroni, we use the distribution of t. So apa beza between T-square interval and Bonferroni method interval? Okay, so actually the simultaneous confidence interval for Bonferroni can be developed that are shorter than the simultaneous T-square interval. So dia punya interval untuk Bonferroni method ni lagi shorter, lagi kecil, ataupun so we can say that it's more precise lah, sebab dia punya confidence interval tu lagi narrow. So it is more precise than the simultaneous T-square interval. So because of that, most of the researcher, we usually use the Bonferroni method to calculate the simultaneous confidence interval. Okay. Alright, so let's see the formula. Formula of the Bonferroni method. Dia sama like tadi in simultaneous T-square interval, cumanya bezanya dekat sini when we replace from F distribution kepada T distribution. Okay. Okay. Let's see the same example. Tadi kita nak test hash note mean vector for 50 and 10. Given x bar vector, given variance covariance matrix. So we apply the formula. First you cari dulu ni T, value of T 2.539 using the T table. Nanti check betul tak, you akan dapat macam tu. Okay, P here adalah number of variable and N adalah sample size. Okay, tadi gunakan T-square interval. T-square interval, we have the value of F table adalah 8.29, but now gunakan T distribution, T table, the value is 2.539. Because of that, the interval, when we are using Bonferroni method, the interval will be narrower ataupun shorter, so it is more precise. Okay, just apply the formula macam tadi, so you get this confidence interval. Okay, let's see. Sama juga, you can interpret the value of confidence interval macam biasa. So kalau kita tengok here 4 termasuk juga kan in the interval. Mu 50 includes in this interval, and value 10 is includes in the interval, so we can make the same conclusion as the mean vector is the possible value for the population mean. Okay, so let's see the difference between T-square interval and Bonferroni interval. Okay, if you can see, the Bonferroni interval falls within the T-square interval. Betul tak? Falls, all of this, it's for Bonferroni falls within the T-square intervals. The two Bonferroni interval is contained in the rectangular region by the two T-square interval. And then from here we can see that Bonferroni interval provide more precise estimates than the T-square interval, because it have the shorter or more precise interval than T-square interval. Okay, how about when we are dealing with the larger sample size? Okay, so this topic is about the large sample inferences about a population mean vector. Okay, as you know from your previous knowledge, when the sample size is large, the test hypothesis and the confidence region for mean can be constructed without the assumption of normal population. So you also know that before this, the serious departure from a normal population can be overcome by large sample size. We can assume any distribution or data can be normal distribution if large sample size involved. Okay, so for this topic, we will use for all large sample inferences about mean, we will use based on the chi-square distribution. Okay, from the previous chapter, you also know, you also remember this theorem, right? Which is, it is known that when x bar is distributed with normal population with mean vector mu and covariance is big sigma divided by n, then this term, which is the square distance, will have a chi-square distribution, same as this term, and x bar minus mu transpose tadi sigma inverse here, big sigma inverse. Now variance covariance inverse multiply x bar minus mu also have the chi-square distribution. These two theorem you have learned before this in the previous chapter. Cuba tengok balik. Okay, so so for this chapter, previously we have testing the mean vector, whether the mean value mu naught is plausible for the mean multivariate population, right? So when n minus p is large, the hypothesis of hash naught, which is the mean vector mu equal to mean vector mu naught, will be rejected if the square distance more than chi-square with p degree of freedom, because of this theorem that you have learned before this. Okay, so for n is large, okay, when we are dealing with the large sample, to reject the hash naught of mean vector equal to the value of mean vector mu naught, when the square distance is more than chi-square p. Before this, the t square here, we will reject hash naught when the t square here more than the value of c square, right, which is the f distribution. But for large sample, we compare with chi-square distribution with degree of freedom p, which is the number of variables, and then we can make the conclusion as usual, like before this, whether the mean vector is plausible or not for the mean multivariate population. Okay, that one is for hypothesis testing, to know whether the mean vector value of the mean vector is a plausible value for the mean population. Okay, so another one adalah when we want to find the confidence interval. Okay, in condition of large sample size. Alright, so this is the formula. X bar plus minus, we will use the chi-square distribution here. Before this, in t square interval, here we use the f distribution, right? We will use the f distribution, but now when we are dealing with the large sample size, here we replace with chi-square distribution with p degree of freedom. Yang lain-lain sama, which is here is also the square root of the variance for the first variable, here variance for the second variable, and so on. Okay, so that one is the confidence interval. Okay, remember to find the confidence interval we have two methods, whether you use t-square interval or Bonferroni confidence interval. Same here when we are dealing with the large sample size, whether we will use this formula or Bonferroni confidence interval. Okay, which is we replace the square root of the value from chi-square distribution, we replace with the value from standard normal distribution table, which is z alpha over 2 multiplied by p. Yang lain-lain sama, here x bar, here is the variance for the corresponding variables. Just replace the chi-square with the standard normal distribution. Yang lain-lain, you want to interpret the confidence interval is the same like before this, or also you can use the confidence interval to conclude about the plausible value of the mean population pun boleh juga. Alright, so basically that's all for chapter 5. So we are finished for chapter 5. Okay, thank you.